This is the first video of the thought-provoking series. As I mentioned in the previous introduction video, I was going to start off with insignificance of how just the general scale of everything in the universe, or at least something to begin with. So let's start. Right here we have an atom. It's roughly 10 to the negative 8 centimeters big, so yeah, it's obviously a little bit bigger. Press Command plus a few times, but this is an atom, so think about that. Now, you can't really get an idea of how small an atom is. Any object that I show you is going to have a lot of atoms. This is going to have a lot of atoms. This is going to have a lot of atoms. And this is going to have a lot of atoms. So how about, let's take something small. Say a pinhead. How many atoms do you think are in here? Okay, you probably said nothing, but there's 5 million atoms that can be squished into that space, assuming they're hydrogen atoms, of course. Continuing with our pin analogy, let's look at a city such as New York. Let's assume that every single one of the residents within New York owns a pin. Since the population is 8.538 million, we'd assume that there'd be 8.538 million pins. And since the average pin is 1.5 millimeters, if we stacked every pin owned by every person in New York City, if we stacked it on top of each other, that'd be 12 million millimeters. Or in feet, that would be 39,370 feet. And for comparison, that would be 10,000 feet higher than Mount Everest. So that's pretty tall. We're still in the range of what we can comprehend using pins. So we're going to need to move on to something of a larger scale. Eventually, planet size is going to be too small. So let's start. Just to make sure that you can visualize the immense size of Mount Everest, think about how long it takes to actually climb it. According to Google, it takes about 2 months to climb it. That is a pretty tall mountain. So now let's look at the size of Earth using Mount Everest as a scale. Mount Everest is 29,000 some odd feet. Now, if we look at the circumference of the Earth from pole to pole, so that'd be from the North Pole to the South Pole, is 24,811 miles. Or in feet, it's 131,007,000 feet. That's pretty tall. So, how many Mount Everest do you think it would take to go from the South Pole to the North Pole? To answer your question, it would take roughly 4,513 Mount Everest. And that would take 9,026 months to climb, or roughly 700 plus years. You'd pretty much give up after about 10 Mount Everest, so that would stretch. If this was at the equator, it would stick out an Earth to the left or right, so that wouldn't exactly be good at all. Luckily, I do not think it would hit the moon, so that would not be a problem. Now, at this point, Mount Everest is too small to use as comparison for anything, so let's switch to the planet Earth itself. The Earth is about 12,756 kilometers, or 7,926 miles in diameter. So Earth is the third planet from the Sun. It's the only planet we know that's capable of supporting life, as we know it so far in 2017, and it's not the biggest planet in the solar system. The biggest planet in the solar system is Jupiter. The second biggest is Saturn, and so on and so on. The Sun, however, dwarfs all of these in comparison. The Sun, in fact, has a diameter of 864,575.9 miles. That completely dwarfs Earth. In comparison, here's a picture. Sun looks pretty big, doesn't it? The thing is, though, our Sun isn't even big when compared to other stars. So let's compare the Sun to, let's say, to Sirius. Sirius would appear noticeably larger than the Sun, but we'd still be able to see the Sun. Let's go to Rigel. In comparison, Rigel is the size of a watermelon to these grape-sized stars, and then the Sun at this point is like a poppy seed. So let's look at Betelgeuse. In comparison to this, it's like a 10-foot beach ball. A huge, huge beach ball. It completely dwarfs all other stars around it. When we're comparing the Sun or Sirius or Aldebaran or Pollux, or all these stars are a lot smaller than Betelgeuse. But Betelgeuse itself isn't that big when you look at the bigger picture. The bigger picture, of course, being an even bigger star, which is called VY Canis Majoris. This star is so big that if you set our Sun next to it and took a picture from far enough away that you could capture the full star, the Sun would take up less than a pixel. That is insane. You could have a super high resolution image, you could see everything about that star, and then the Sun would almost be invisible because of how small and how VY Canis Majoris' light would just blot out anything the Sun could put out. But even then, this star is still small when it's compared to the smallest galaxy that we know of. Okay, after doing a quick Google and Wikipedia search, I found out that Seg2 is the smallest known dwarf spheroidal galaxy in our known universe. It's in the constellation Aries. For astrologists, I don't know if you do that thing or... Okay, but it's 34 parsecs in diameter. So when we equate that to miles, it's 6.519 e plus 14 miles. When we put that into a more manageable number, it is 651,900,000,000 miles in diameter. When we compare that to, let's say, VY Canis Majoris, we find out that its diameter is 1,227,829,475.861 miles. So still, that huge star that dwarfs our Sun in comparison is tiny compared to this tiny galaxy. Our galaxy, on the other hand, dwarfs this galaxy. So let's get to the Milky Way galaxy now, which we reside in. At this point, it gets too hard to actually use miles, so we'll instead use light years. As you know, of course, light travels 186,282.397 miles per second within a vacuum. Space isn't a complete vacuum, but we'll just keep that as our base measurement for now. Since light is the fastest moving thing in our universe, we'll just use that. So our Milky Way is roughly 100,000 light years. So the distance that light travels in a year is times by 100,000, and then you get the size of our Milky Way galaxy. And our Milky Way galaxy is nowhere near the size of the biggest ones. The biggest galaxy in our known universe is NGC 6872. Flashy name. but it's also known as the Condor Galaxy. So here's a picture of it. It is 160 kiloparsecs, so that's pretty big. 1 kiloparsec is equivalent to about roughly 3,260 light years. So if we times that by 160, then we get 521,600. So that is it's pretty big, so yeah, it is pretty big. It takes roughly 500,000 years to go from one side of that galaxy to the other, so that's pretty far if you think about it, but still, that's dwarfed in comparison to the size of the observable universe. The observable universe, on the other hand, is about roughly 93 billion light years, so we went from 500,000 light years to 93 billion light years, so that's pretty far. Keep in mind that our universe is only about 13 billion years old, so there hasn't been enough time for light from one side to travel to the other side, so that's pretty far. And as far as science is concerned, our universe is still expanding. Still. So just think about that. When you go way back to where we started, way back to when we were still at Earth, you thought that you still mattered. The average person is a little less than 6 feet tall. We've been talking about the distance that light travels in billions of years. Before that beam of light has even a chance to go 1/100th of the span of one of these galaxies, you'd be dead. Your children's children would be dead. Your 100 times grandchildren would be dead. Earth would be gone. It's unimaginable how big space really is. It's absolutely mind-blowing. Think about this. The farthest that humans have ever gone is a little bit beyond the moon or the dark side of the moon. That's how far we've gone. And that was within the span of a few days, traveling as fast as human technology allowed for. But still, we haven't even gone to our nearest planet. We haven't even gotten anywhere near our closest star. The Voyager probes, they were sent out in the 1970s. They've barely left our solar system. They're going to continue for another 300,000, 40,000 years until they get to another star, another solar system. By then, everybody who was associated with the project will be dead. Their great times 100 grandchildren will be dead. It's insane how big space is, and it just keeps continuing to expand. When people concern themselves with tiny things that won't matter in the long run. It won't matter because in terms of universal, in the universal scale, nothing here will really have any impact on anything that happens in the universe. Pretty much anything that humans are capable of doing will not impact anything at this time in the universe. Pretty much nothing would happen. We're in our own bubble region of space that's comparable to an atom going off and doing its own thing. Not even that, an electron doing its own thing in its own space, way off somewhere in the middle of nowhere. It's unimaginable. just how big space is. You think that you can comprehend this, but you cannot. You cannot understand how big space is. It is unimaginably huge. There, I hope you enjoyed this video. Look out for other videos, the thought-provoking series. I have a few ideas for that, and with a story told through stock photos part 4, that's still in production. That should be out soon, hopefully before Christmas or during Christmas when I get more time. So, thank you.